Hi everybody, welcome back for note 6.3. In today's notes, we are going to be talking about rational functions, the attributes of rational functions, and how to graph rational functions. Before we begin, let's revisit some vocabulary that we're going to need to be successful in this lesson. So the first blank is a function that can be written in the form of p of x over q of x. Now we remember from our 6.2 notes that that is a rational function. So basically a rational function is a function in which you have a polynomial in the numerator and a polynomial in the denominator. The next one says that a point of discontinuity is the x-coordinate of a point where the graph of a function is not continuous. Now, if a graph is continuous, that means I can draw the entire graph without having to pick up my pencil. Not continuous means we're going to have to pick up our pencil at different points to continue drawing that graph. So we're going to talk about two kinds of discontinuities today. We're going to talk about asymptotes, and then we're also going to talk about holes in our graph. So we kind of dipped our toes into working with asymptotes when we talked about 6.2 when we had the vertical and horizontal asymptotes. So we're going to work more with that today, but then we're also going to introduce how do we get a hole in our graph. So let's talk about removable and non-removable discontinuities. A removable discontinuity is a hole in the graph. It is a hole in the graph. The hole occurs in the equation where there is a common factor in the numerator and denominator, thus the original function is undefined at a specific x value. So there is a hole when you have a common factor on the top and the bottom that will cancel out. So let's look at an example. If we have f of x equals x minus 2 times x plus 3 all over x plus 3, you'll notice that we have an x plus 3 in the top and the bottom. So therefore, those two factors cancel out. So we redefine our function to be f of x equals x minus 2. Now here's how we get the hole in our graph. We take the factor that was canceled out and we set it equal to 0. So we take the factor that was canceled out, we set it equal to 0, and we solve for x. So I've got the x-coordinate of the hole, but the hole is a coordinate point that's got an open circle instead of a closed circle. So we have to find the y value as well. So we take that x value we just found and we plug it back in to the simplified equation. So we're going to take negative 3 and we're going to plug it back into x minus 2. So negative 3 minus 2 is negative 5. So that tells me that the hole in my graph occurs at the point negative 3, negative 5. Okay, so revisit those steps. You cross out the common factor and rewrite the new function. You take the common factor that was canceled out, you set it equal to 0, you solve for x. You then take that x and plug it back into the simplified function, and there's the coordinate for the hole of your graph. Now, one way I always tell my students to understand the difference between removable and non-removable, I have actually, if you look at this original function, I actually removed x plus 3 from the function. So I removed a piece of the function, therefore creating a hole. So if I have a hole in my graph, that is from a removable discontinuity because I removed that from my equation. Now, non-removable, those are asymptotes. Okay, non-removable discontinuities are asymptotes. So if we look at this function, f of x equals x minus 2 over x minus 5, the denominator can never, ever, 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 never, ever equal 0. You are not allowed to have a 0 in the denominator. So the way we find out how are we going to have a vertical asymptote is we set that denominator equal to 0 and we solve for x. So obviously nothing can cancel out here. So we take the whole denominator, x minus 5, and we set it equal to 0. And so we find out that if x equals 5, 5 minus 5 is 0. So we can't have that. So we are going to have a vertical asymptote at x equals 5. And again, this is non-removable because we didn't actually remove anything from the equation. We simply took the denominator, we set it equal to 0, solve for x, and that's the equation of our vertical asymptote. Okay, on the last slide we talked about vertical asymptotes, but we also know that horizontal asymptotes exist as well. So to find the equation of the horizontal asymptote, we are going to be comparing the largest exponent on top to the largest exponent on bottom. We're only dealing with the exponents. So exponent on top, largest exponent on bottom. So that's what we mean when we say if the exponent is. So if the exponent is Bobo, and you're like, what? Bobo stands for bigger on bottom 0. Bigger on bottom 0. So let's look at an example of bigger on bottom. So we have y equals 2x plus 3 over 3x squared. Now, the exponent on the top, that is 1. Okay, the exponent on the top is 1, and the exponent on the bottom is 2. So 2 is bigger than 1. So the exponent is bigger on bottom, therefore your horizontal asymptote is y equals 0. So if the largest exponent on bottom is bigger than the largest exponent on top, that's Bobo, and therefore your horizontal asymptote is y equals 0. Now let's talk about BOTN, B-O-T-N. That stands for bigger on top, none. Or you could even say bigger on top, no asymptote. So let's look at an example of BOTN. So you see right here that on the top we have an exponent of 2, and on the bottom we have an exponent of 1. So 2 is bigger than 1. So the exponent on top is bigger than the exponent on bottom. So bigger on top means that there is no horizontal asymptote. Now, for the last one, EATS DC. EATS DC stands for exponents are the same, divide the coefficients. So here's what an example of EATS DC is. My biggest exponent on top is a 2, and my biggest exponent on bottom is a 2. Since they are the same, I'm going to divide the leading coefficients. So they're both 2, so exponents are the same. Divide the coefficients. So in this case, I would say y is equal to 6 over 3, which is 2. So let's revisit this. I want to take a little extra time on this because this is a huge component of graphing rational functions. So BOBO stands for bigger on bottom. That means the exponent on bottom is bigger than the top. So bigger on bottom, 0. Y equals 0. Botan. Botan stands for bigger on top, no exponents. So my exponent is bigger on the top. So bigger on the top, no horizontal asymptote. And then lastly, eats DC. Exponents are the same, divide the coefficients. So these are both squares on top and bottom. So I would take and I would divide 6 by 3, and that would give me the equation for that horizontal asymptote. And so that's why you'll hear us in this lesson, is it Bobo, Botan, or eats DC? And when we say Bobo, Botan, eats DC, then you know we're talking about horizontal asymptotes. And then just to remind you, for the vertical asymptote, you are going to simplify the functions on top and bottom. That means you will factor them and cross out any common factors. Then you will set any remaining denominator factors equal to 0 and solve for x. Okay, so before you look at vertical asymptotes, you need to make sure your function is simplified as much as possible, and then set any remaining denominators equal to 0. Okay, let's look at how we write domain and range for our rational functions. You're going to see that it looks very familiar to how we wrote the domain and the range for our reciprocal functions. And that's because it is. Because if you remember, domain of a reciprocal function was negative infinity to the vertical asymptote union vertical asymptote to positive infinity. So you'll see that it is basically the same notation. It's just that now, because we have holes, we can't say strictly that it's to the vertical asymptote. Because if it was a hole, instead of being vertical asymptote, it would be the x-coordinate of the hole. Okay? Same with the range. So the range, when we talked about it in 6.2 for the reciprocal function, the range was negative infinity to the horizontal asymptote union horizontal asymptote to infinity. But again, because we could possibly have a hole instead of an asymptote, that horizontal asymptote would become the y-coordinate of the hole. Okay, and again, we use the U symbol to indicate a union of the domain from each of the branches, as well as the range from each of the branches. Okay, so your point of discontinuity could be a hole or an asymptote. If it's an asymptote, then it's going to be negative infinity to vertical asymptote union vertical asymptote to infinity. And then the range would be negative infinity to the horizontal asymptote union horizontal asymptote to infinity. Now, if it was a hole, the domain would be negative infinity to the x-coordinate of the hole union x-coordinate of the hole to positive infinity. The range would then be negative infinity to the y-coordinate of the hole union y-coordinate of the hole to the infinity. Now, don't worry, you're going to get lots of practice writing domains and ranges with asymptotes and with holes in the graph. Now, let's look at this. These are the steps to graph, and I promise you, if you follow these steps, it will make your life so much easier when you go to graph your rational function. Okay, and you follow them exactly. You do number 1 first, then you do number 2, then you do number 3, then you do number 4. Okay, I promise you, if you follow this step-by-step method, it's going to make graphing your rational functions so much easier. So the first thing when you're given a graph, or excuse me, when you're given an equation or you're given a function, the very first thing you do is you look for your horizontal asymptote. Is it Bobo? Is it Botten? Is it HDC? So we're going to look and compare the biggest exponent on top to the biggest exponent on bottom. So that's the very first thing before you do anything else, is you look and see, is there a horizontal asymptote? The second thing you're going to do is you are going to see if you can simplify the function by factoring and canceling out any common factors in the numerator and the denominator. So take, for example, this function I've given you, x plus 1 times x minus 4 over x plus 1. So you see that the x plus 1 cancels out. My simplified function is f of x equals x minus 4. Then I take x plus 1, I set it equal to 0, I get negative 1, and then I take that negative 1 and I plug it back into x minus 4 to get a y coordinate of negative 5. So I would say, okay, well, this function has a hole at negative 1, 5. Sometimes you might have a hole in the graph, sometimes you won't have a hole in the graph. It's just dependent. It's not mandatory that you have a hole in the graph. It's just if you have something cancel out, there's a hole. The third thing you're going to do is you are going to set the denominator of the simplified function equal to 0 and solve for x. So you would see, like, we've already got the function simplified when we were looking for the holes. So in the example for number 2, there wouldn't be a vertical asymptote because there is no denominator. But if your function doesn't simplify and you have a denominator, or if it does simplify and you had a denominator left over, then you're going to have a vertical asymptote. So if there is no x in the denominator of the simplified function, then there will be no vertical asymptote. So if you simplify the function and you don't have an x in the denominator, you don't have a vertical asymptote. The other case is if there is an x in the denominator of your simplified function, then there will be a vertical asymptote. So if you simplify your function and you still have an x in some shape or form in the denominator, then you're going to have a vertical asymptote, and you just set it equal to 0 and solve for x. And then the last option is if you can't simplify the function, then you just use the original denominator. So you've got 3 cases for your vertical asymptote. If you simplify it and there's no x in the denominator, then you don't have a vertical asymptote. If you do simplify it and you have an x left over, then you're going to have a vertical asymptote. Or if you can't simplify it at all, then you're just going to use your original denominator, set it equal to 0, solve for x. There's your vertical asymptote. So we've looked for a horizontal asymptote, we've looked for holes, we've completed the third step for getting the vertical asymptote. Now we're going to do a table of values. The rational functions don't have a parent function that we can shift up, down, left, or right. So here's how you're going to come up with your table of values to graph. What you're going to do is you are going to put you're going to create a table with 5 rows. So you're going to need 5 different x's. And you're going to put your vertical asymptote right in the middle. And the y value for the vertical asymptote is undefined because when you use that x value, it's going to make that denominator go to 0. So can't have a 0 in the denominator, so it's vertical asymptote undefined. Then you're going to pick 2 values to the left of vertical asymptote and 2 x values to the right of the vertical asymptote. Now guys, let me just be straight up honest with you guys. Please pick integers. Do not pick decimals. Do not pick fractions. Pick integers. So you're going to pick 2 integers to the left of the vertical asymptote and 2 integers to the right of the vertical asymptote. I always pick the 2 to the immediate left and the 2 to the immediate right, because that way my numbers stay a little bit smaller and it's easier to calculate. Then, after you get your 4 values, you're going to take each x value and plug it into the simplified function. Or the original if it couldn't be simplified. So you're going to take each x and you're going to plug it into the simplified function if you simplified it. Or if you can't simplify it, you're going to plug it back into the original. Okay? Just remember that the vertical asymptote undefined is right there in the middle. So again, if you follow these steps, it's going to make your graphing so much easier. Let's look at our first example. Okay, we got to look at our first example. So we have f of x equals x plus 1 over x plus 4 and then plus 2. So the first thing we want to do, remember, go back to your steps. The first thing we want to do is we want to look and see, is there a horizontal asymptote? So I'm going to do Bobo Botten eats DC. So I look at the exponent on the top, and it's 1. I look at the exponent on the bottom, and it's 1 as well. So they are the same, so it's eats DC. And so we are going to take the leading coefficient, and we are going to divide them. So it's going to be 1 over 1. But we also have to add the constant 2. Okay, so we have to add that constant 2 because Bobo Botten eats DC only applies to this. So this is like eats DC plus 2. So again, Bobo Botten eats DC only applies to the fractional part. If you're adding a constant on to the end of your function, you have to take that into account when you are calculating the horizontal asymptote. So we are going to divide the coefficients to get 1, and then we are going to add 2. So 1 over 1 plus 2. And let me erase these pen marks so you can see that. So 1 over 1 plus 2. Well, 1 over 1 is 1. 1 plus 2 is 3. So as soon as you find each piece of information, go ahead and plot it on your graph. So I have each DC plus 2, so that gives me a horizontal asymptote of 3. So I'm going to graph it. And ladies and gentlemen, you want to use a dashed line, please remember to graph your horizontal asymptotes because nothing exists at that asymptote, okay? So we've completed the horizontal asymptote. Is anything going to cancel out? Well, x plus 1 is as simplified as it gets, and x plus 4 is simplified as it gets. There's no common factor to cross out, so there is no hole because nothing factors out, and there's nothing that will cancel, so there is no hole. So we've done the horizontal asymptote, we've done step 2, looking for the hole, and then step 3 is the vertical asymptote. So vertical asymptote says take any remaining denominator and set it equal to 0. So I'm going to take x plus 4, set it equal to 0, and I get x is negative 4. Okay? So I'm going to go to negative 4 and I'm going to plot a vertical asymptote. Okay, so step 1, horizontal asymptote. Step 2, was there a hole? Step 3, vertical asymptote. Step 4 is our table of values. Our table of values. So remember, vertical asymptote and undefined go right there in the middle of my table. Negative 4 and undefined go right there in the middle. Now I'm going to pick 2 x's to the left and 2 x's to the right. So immediately to the left of -4 is -5. And immediately to the left of -5 is -6. Now let's return back to -4, and we're going to go 2 to the right. So immediately to the right of -4 is -3. And to the right of that is -2. To get the corresponding x values, or excuse me, the corresponding y values, to get the corresponding y values, anywhere I see an x, I'm going to plug in that x value. So let's do -6. So we would do -6 plus 1 over -6 plus 4 plus 2. So -6 plus 1 is -5 over -2 plus 2. Now, that would become 5 over 2 plus 2. So you can change it to a decimal and say that that's 2.5 plus 2, and you get 4.5. When we're plugging these in to calculate the y values, it's okay to use decimals, because decimals ultimately are a little bit easier to graph, and it's easier for us to have like a visual of what they're talking about. Now we try -5. So -5 plus 1 over -5 plus 4 plus 2. So that gets me -4 over -1 plus 2. So 4 plus 2 is 6. And then you just repeat the process for -3 and -2. Okay, so now that we've got our asymptotes, we've checked for any holes in the graph, we've got our table of values, we are ready to plot these points. So I'm going to plot -6, 4.5, -5, 6, -3, 0, and -2, 1.5. Now, all we have to do is connect the dots and hug those asymptotes. So connect the dots and hug those asymptotes. And that's your graph of the rational function. Now, let's talk about domain and range. So our domain is, if you look here, our domain is -infinity to 4, -4, sorry. So -infinity to -4, and then we have to stop. We have to kind of jump to the other side of the asymptote and say -4 to infinity. So -infinity to -4, jump over, and then go -4 to infinity. So that's the domain. Let's talk about the range. So the way we define the range is I go from -infinity up to 3, and then 3 to infinity. So the range is the union of -infinity to 3, and then 3 to infinity. And so that's how I come up with the range. So a lot of this is similar to the reciprocal function, because if you remember, the reciprocal function is a special type of rational function. And your asymptotes are non-removable discontinuities. Asymptotes are always non-removable because they didn't actually take anything away from the function. Okay, let's look at another one. They want us to graph y equals x squared plus 2x minus 3 divided by x plus 3. So let's go back to our steps. The first thing we're going to do is we are going to look for the horizontal asymptote. So Bobo Bottom eats DC. Bobo, is the exponent bigger on bottom? Well, my biggest exponent on top is 2, and my biggest exponent on the bottom is 1. So it's definitely not bigger on bottom. Bottom, bigger on top. Well, the exponent on top is 2, and the exponent on the bottom is 1. 2 is bigger than 1. So that tells me that it is bottom, because there is no, and that tells me too that there is no horizontal asymptote. So bigger on top, because squared is bigger than the first. So bigger on top, no horizontal asymptote. Step 2, we're going to look for holes. But remember, when you're looking for holes, you're going to have to completely factor. So we're going to have to factor the tops and the bottoms if necessary. So you're going to have to revisit your factoring skills. I know, you're so excited. Okay, so if we factor the top, what two numbers multiply to make -3 that add to make +2? That's right, +3, -1. So that becomes x plus 3 times x minus 1 over x plus 3. Okay, and I see right away, oh my goodness, how awesome! X plus 3 cancels. So to get the coordinate of the hole, I have to take x plus 3 and set it equal to 0. Now my simplified function is going to be y equals x minus 1. That's really critical that you write that simplified function. So now we're going to take x plus 3 and we're going to set it equal to 0. So x equals -3. But then you remember, okay, so the x is -3, but I've got to find the y. So I'm going to do -3 minus 1 and get -4. So that tells me that I am going to have a coordinate, that the coordinate of the hole is at -3, -4. So the coordinate of my hole is -3, -4. Just to review you on how we got that, x plus 3 equals 0, because it crossed out. And so that gave me -3. And then I took -3 and plugged it back into the simplified function, and that got me -4. So I do have a hole at the coordinate -3, -4. Now let's talk about, so we've done horizontal asymptote number 1, holes number 2, number 3 is vertical asymptote. So since I simplified this function, I have to look at the simplified function. My simplified function does not have a denominator. There is no denominator in my simplified function. So therefore, I do not have a vertical asymptote. So when I look at the simplified function, I'm like, oh my goodness, that is a linear function. That's a line. It's simplified to become a line. So what I'm going to do is I'm going to plot the hole on my graph. And again, please don't color it in, because if you color it in, it's no longer a hole. So you put an open circle at -3, -4, and then you just apply your slope. Or you could go to -1 and go up 1 over 1. You're still going to intersect the hole. Or you can start at the hole and go up 1 over 1. And I did 2 points on either side, and then I connected the dots to make a line. Now, here is a huge pet peeve of teachers when we're graphing rational functions with holes. You always are tempted to just draw boop straight through that hole. Do not, please do not draw straight through that hole. So you can draw your line up to that hole and then jump over it and go to the other side and continue up. But do not draw your line through your hole, because the minute you do that, that point ceases to be a hole. It becomes a continuous point, and then your graph is incorrect. So we don't want to have to count your whole graph wrong because you drew through the open circle on your graph. So never ever draw straight through the hole. You want to make sure that it is an open circle. Okay, so now let's talk about domain. Okay, so when we talk about domain, as I come from the left, I'm going to -infinity. but I stop right there at the whole, which is -3. So I'm going to go -infinity to -3, jump over to the other side, and then say -3 to infinity. Just like with the asymptote, except instead of an asymptote, it's a whole. Okay? So that's how I get -infinity to -3. Now for the range is the y's. So I'm coming from -infinity. I stop at the whole because I can't, that's like, kind of think about it like a crater in the ground. Can't like go in the crater. So I'm going to go from -infinity to the y coordinate, which is 4, and then -4, excuse me. So it's -infinity to -4, and then at -4 all the way to +infinity is the other piece of the range. So again, your range is the y's, so it's -infinity to -4, -4 to +infinity. Now, is this whole a removable discontinuity, or is it a non-removable discontinuity? So again, let me ask that without changing the word on you. So is this whole, is it a removable or non-removable discontinuity? And the answer is it's a removable discontinuity because I actually removed x plus 3 from my equation. All right, let's look at our next example. Y equals x squared plus x minus 12 all over x squared minus 4. First thing we look for is horizontal asymptote. Step 1 is horizontal asymptote. So is this Bobo? Is it Botan? Is it each DC? Well, the biggest exponent on top is a 2. The biggest exponent on bottom is a 2. So that's each DC. Each DC. Exponents are the same. Divide coefficients. So we're going to divide the leading coefficient. So they're both 1s. So I get 1 over 1, which is 1. So my horizontal asymptote is y equals 1, and I plot it on my graph. Excellent. We've got the horizontal asymptote. Now step 2 is, let's look and see, do we have any holes in our graph? Well, to determine a hole, we have to factor top and bottom. So in the top, what two numbers multiply to make -12, then add to make +1? And that's -3 and 4. Now on the bottom, that's a difference of 2 squares. So that's going to be an x plus 2 and an x plus 2, x minus 2. So x plus 4 times x minus 3 over x plus 2 times x minus 2. Nothing cancels out. There is no common factor in the numerator and denominator. So since nothing's going to cancel out, there is no hole in the graph. Nothing cancels out, so there is no hole in the graph. Let's talk about vertical asymptotes now. Now, since the function didn't simplify, I just have to take the bottom, set it equal to 0, and solve for x. But think about it. You've already got it factored, so I wouldn't go all the way back to the original denominator. I'd use my factored denominator. And you're like, wait a minute. This problem has two factors. So guess what that means? You're going to have 2 vertical asymptotes. So if you have more than one factor in the denominator, however many factors you have, that's how many vertical asymptotes you're going to have. So I take x plus 2 and set it equal to 0, and I take x minus 2 and set it equal to 0. So I get x equals 2 and x equals negative 2. Yay! The negative 2 came from x plus 2 and the positive 2 came from x minus 2. So I am now going to plot two asymptotes. Okay, so I've done horizontal asymptote, I've done the hole, which there wasn't a hole in the equation, and then I've done the vertical asymptote. So step 4 is my table of values. Now, your table of values on this one is going to look a little bit different due to the fact that you have two vertical asymptotes, okay? So again, we checked for the horizontal asymptotes, we checked for a hole in the equation, which there wasn't, so there's not going to be a hole in our graph. We've done the vertical asymptotes, and now we have to do a super special table of values. Super special table of values. Now, when you have two vertical asymptotes, you are going to need a total of, you're going to need 2 to the left of the first asymptote. You're going to need 2 to the right of the right asymptote, and you're going to need 3 in between. So if you have two vertical asymptotes, you're going to pick 2 to the left of the left one. Then you're going to pick 2 to the right of the right one. These are the vertical asymptotes. And then you're going to pick 3 in between. So 2 to the left of the left asymptote, 2 to the right of the right asymptote, and 3 in between. So what I'm going to do is I'm going to come down 2 spaces from the top, and I'm going to put my negative 2 in. And then 2 spaces from the bottom, and then I'm going to put my positive 2. So just remember, if you have two vertical asymptotes, it's 2, 3, and 2. Okay? I'm sorry if I get a little excited doing this problem. I love these kind of problems. Okay, so again, we're going to pick 2 to the left of the left vertical asymptote. So that would be negative 3, negative 4. Then we're going to pick 3 in between. So that would be like negative 2, negative 1, 0, and 1. And then 2 to the right. So 3 and 4. Now, I've got all seven of my x coordinates. Again, remember, negative 2 is undefined, positive 2 is undefined. So we've got a total of 7 x's that we need to plug in. Now, I always get the question, does it matter if I plug it into the factored form, or does it matter if I plug it into the original? Technically, it doesn't matter. Technically. If you factored it right. If you factored it right, it doesn't matter. But if you're concerned about your factoring, I would go back and plug it into the original. But as long as your factoring is correct, it doesn't matter which form you plug it into. So you're going to take negative 4 and you're going to plug it into every place you see an x and simplify. Then you're going to take negative 3, plug it into every x and simplify. So we know how to plug into an equation. So I'm just going to give you the values after I plug in. And you're like, well, negative 3 gave you negative 1.2 and 1 gave you 10 over 3. Does it matter which way I write my y's? Technically, no, because 10 over 3 is 3.3, and it's okay to have decimals in your table because you're just graphing them. You're just graphing. So instead of 10 over 3, if you wanted to write 3.3, that's going to be perfectly fine with us. We're not going to split hairs over that. So we are going to plot all 7 of those points. And then we are going to connect the dots and we are going to hug those asymptotes. Okay, so you'll see that in this example, we had two vertical asymptotes, which gave me two branches and a parabola in the middle of those two asymptotes. So we have two branches and a parabola in the middle. So let's talk about, let's talk about our domain. So our domain, we're coming from negative infinity, and we stop right there at -2. So there's our first piece. And then here in the middle, we go from -2 to +2. There's a second piece. And then we go from +2 to infinity. So let's look at that again, because I want to make sure that you guys get this. So coming from negative infinity, we stop at -2. Then we have -2 to +2. Then we have +2 to infinity. So that's why our domain looks like that. Now let's talk about the range. So the range is coming from negative infinity. It stops right there at 1, and then it picks up on the other side of 1 and goes to infinity. So the range only has two pieces, negative infinity to 1 and 1 to infinity. Now, these are asymptotes. So are they removable or non-removable? And the answer to that question is they are non-removable, because I did not remove anything from my equation. Okay, let's look at this example. Now I know what you're probably thinking. You're like, oh my goodness, those are the 6.2 functions we looked at. That is exactly what that looks like. And you're right, it is. So the reason we're doing another one like this, so this is a reciprocal function, which is a special type of rational function. The reason we're doing this one is because I want to show you that you can graph this. Yes, we could graph it like we did in 6.2, but you can also graph it using these rules that we've learned today. So if you want my opinion, if you're like, dude, I only want to remember one way, I only want to have to think about one way to graph any kind of rational function, you want to use the process that we did today. Because the process that we did today will graph any generic rational function, and it will also graph reciprocals. However, the method we learned in 6.2 will only work for ones that look like 6.2. So that one where we had two vertical asymptotes, you could not use your reciprocal function rules on that. It wouldn't work. So, like I said, if you only want to remember one way to graph any kind of rational function, then you need to focus on the way we do it today with 6.3. That's just my, that's just probably the easiest way to do it. Okay, so yes, we could graph this with 6.2, but let's see how we graph it using our rules today. So first step, always, always, always. Bobo, Botan, eats DC. Is it Bobo? Is it Botan? Is it eats DC? So let's look at the fractional part of the function here. So we look and you're like, well, there's no x in the numerator. Well, you're right, there is no x. Technically, it's x to the 0th, right? X to the 0th is 1. And then the bottom has an x to the 1st. So 1 is bigger than 0, so it's Bobo. Now remember, Bobo only applies to the fraction part. So this is really going to be Bobo minus 3. So it's going to be, the Bobo part is going to be 0. And then we have 0 minus 3. So my horizontal asymptote is going to be y equals -3. So let's plot that dude. Okay, now let's look and see, are there any holes? Well, this is about as simplified as it gets. So nothing cancels out, so there are no holes. Let's talk about vertical asymptote. It didn't simplify, so I look back to my original function and I'm like, oh my goodness, x plus 2. So x plus 2 equals 0, so x equals -2. Now we're ready to come up with our table of values. So remember, -2 and undefined go in the center, and then we pick 2 to the left, so -3, -4, and 2 to the right, -1, 0. Then we take and we plug each x into the above equation and we solve for y. When we do that, we get the following y values. Now I'm ready to plot my points. Connect the dots, hug those asymptotes. All right, so here's our graph. Let's talk about our domain. Our domain is going to be from -infinity to -2 and -2 to positive infinity. And then our range is from -infinity to -3, -3 to positive infinity. So there's our domain and range. Now this graph right here had asymptotes only. So is that removable or non-removable? The answer is non-removable. Now, you may wonder, well, can I have asymptotes and holes in the same graph? And the answer is absolutely. It's a case-by-case basis. There is no hard and fast rule to, yes, you can only have asymptotes, or yes, you can only have a hole in the graph. You can actually have both types of discontinuities in the same graph. All right, let's look at this example. Y equals x squared plus 3x all over 2x plus 1. So we have to work the steps. The first step is there a horizontal asymptote? Well, biggest exponent on top is 2. Biggest exponent on bottom is 1. So is it Bobo, Botan, or eats DC? And it is actually Botan, because 2 is bigger than 1. So it's Botan, so there's no horizontal asymptote. Now we're going to check for a hole. So I need to see if I can simplify that fraction. So that means I have to factor. Well, look at my top two terms. I have x squared and 3x. I can factor out an x. And all I did on the bottom is, instead of writing 2x, I wrote x times 2 so that you could see that my x's are going to cancel out. So my simplified function is x plus 3 over 2 plus 1. So because x factors out, there is a hole in the graph at x equals 0. So we need to plug 0 in to figure out what the y-coordinate is. So 0 plus 3 is 3. 3 over 2 is 1.5 plus 1 is 2.5. So I know I'm going to have a hole at 0, 2.5. Now let's talk about the vertical asymptote. Now, my simplified function does have a 2, but it doesn't have a variable. So it has a denominator, but there's not a variable in the denominator. So there is no vertical asymptote. So now, the best way to do this is you can actually simplify that function in teal. You can simplify it a bit further. So I'm going to put x over 2, and I'm going to put 3 over 2, and then plus 1. So that becomes 1/2 x plus 3/2 plus 1. I'm going to change that 1 to be 2 over 2. So 2 over 2 plus 3 over 2 is 5/2. And oh my goodness, holy Toledo Batman, it's another linear function. It's an mx plus b. So I'm going to plot my hole. So there's my hole at 0, 2.5. And then, which is actually also the y-intercept of your linear function. And then you're going to go up 1 over 2, up 1 over 2. And then you're going to go down 1 over 2, down 1 over 2. And then I am going to connect the dots. So let's talk about the domain of this function. So this one's going to be, since there's no asymptote, it's going to be negative infinity to the x-coordinate of the hole, x-coordinate of the hole to infinity. So the x-coordinate is 0. So it's going to be negative infinity to 0, union 0 to infinity. Now for the range, it's going to be negative infinity to the y, and then y to positive infinity. Well, the y-coordinate of my hole is 2.5. So it's negative infinity to 2.5, union 2.5 to infinity. And this is a hole, so it is a removable discontinuity. On this example, y equals 6 over 3x plus 3 plus 7. They simply want us to find any asymptotes and or holes in the graph. So we don't have to graph it. We're basically just going to be doing steps 1, 2, and 3. So step 1 is the horizontal asymptote. Bobo, Botan, eats DC. Well, there's not an x in the numerator, but really it's x to the 0th, because x to the 0th is 1. So it's bigger on bottom, so that's Bobo. Bigger on bottom, it's 0. But remember, Bobo only applies to the fractional part. So this is really Bobo plus 7. So that's going to be 0 plus, if you think about it, like a k value. Or you can just say Bobo plus whatever the constant is. So Bobo plus 7. So y equals 7. Now we're going to look for holes in the graph. So, I can factor that bottom to be 3 times x plus 1, but there's no other x plus 1 to cancel out. So nothing's going to cancel out, so there aren't going to be any holes in my graph. Let's talk about the vertical asymptote. So all I have to do is take the denominator, set it equal to 0, solve for x. Okay, when you're doing the vertical asymptote, do not add k. Do not add that constant. You only add the constant to the horizontal asymptote, because adding 7 is shifting your graph up 7. So that's only going to affect the horizontal asymptote versus the vertical. So we're just going to do 3x plus 3 equals 0, and we come up with a vertical asymptote at x equals -1. All right, last example, a little higher order thinking here. So x squared, so let's talk about that horizontal asymptote. Bobo, Botan, or eats DC. It's Botan because the square on the x is bigger than the 1 on the x in the bottom. So it's Botan. Now, this leads us, though, into something that you will talk more about in pre-cal. We just kind of wanted to introduce it to you. When the degree of your numerator is bigger than the degree of your denominator by 1, you have something called an oblique asymptote. So instead of, think about it, instead of a horizontal or vertical asymptote, it's really like a sloped line. So an oblique asymptote is an asymptote that is much like a sloped line. And how you find the equation of that oblique asymptote is with synthetic division. Okay? So you take and you do synthetic division with -3. Okay? So it's just like, guys, this is just like we looked at in 5b, and we did synthetic division when we did x squared minus 2x minus 3 divided by x plus 3, and we did synthetic division. That's all you're doing here. So you bring down the 1. Negative 3 times 1 is negative 3, which gives me negative 5. Negative 3 times negative 5 is positive 15, which gives us a remainder of 12. So remember, synthetic division knocks it down by 1 degree, so that means it would be x minus 5, remainder 12. But remember, we really say 12 over x plus 3. But anyways, so we kind of, when we're talking about the oblique asymptote, we kind of ignore the remainder, and that becomes the equation of our oblique asymptote. And if you were to graph it, this is what your graph would look like. So you can tell there's the asymptote right there. So again, you're not going to be tested over this. You're not going to see it on a quiz or anything. We just wanted to show you so that you did have some exposure to oblique asymptotes, so that when you get to pre-cal, you're not totally like, what? So we just wanted to point that out, that there are other types of asymptotes besides horizontal and vertical. Okay, so that completes our lesson 6.3, guys. I'm sorry that this one ran a little bit longer, but there is so much important information that we had to cover in this that I didn't want to shorten it and then leave y'all short and not have enough information to do the job you need to do. So that's it. Video's over. You may now go work on your homework worksheet 6.3. But guys, please remember to socially distance, 6 feet apart. Wear your masks, wash your hands, use hand sanitizer. Please make good decisions and not hang out in big groups, because we all want to get over this thing and we all want to be back in person eventually. All right, so hang in there, keep up the good work, and we will talk to you soon. Have a good one, guys.